All right, here we go. Unit 4, polynomial functions. So in this unit, we're going to be looking at polynomials of higher degree. So we've looked at quadratics, which is degree 2. So now we're going to look at polynomial functions with higher degrees, such as 3, 4, 5, and 6, and so on. All right, so a little bit of Algebra 1 review. Says Victoria tried to subtract two polynomials. Her work is shown below. So Victoria's work is over here on the left. And it says towards the bottom, it says at which step did Victoria make an error, if at all? Explain your reasoning. All right, so we're going to go through the steps. So if you recall from Algebra 1, first thing you have to do here is distribute the negative sign because we're subtracting the polynomials. So we would rewrite and have k squared plus 2k minus 13. And then minus a negative 3 is going to be plus 3k squared. Minus a positive 9 is minus 9k. And minus 1 at the end. Okay, so step 2. Now we gather our like terms. So our k squareds go together. Our k terms go together. And our constants go together. So if you look at the way they have written out their steps, I'm going to write them out the exact same way they did. So if we put our k squared terms together, we have 1 plus 3 k squared. So that's these terms. So then our next terms, we're going to put our k terms together, which are these terms. So I have a plus 2 minus 9 k. Then our last terms we're going to put together are the constants. So that would be plus negative 13 minus 1. So now if I simplify my parentheses, I have 4k squared. 2 minus 9 is negative 7, so minus 7k. And then plus negative 13 minus 1, so minus 14. So we can see that our k squared term is correct, but then we have these two terms that are incorrect. So the place she made her error, if we look right here, she has a positive 2 plus 9, and we have a 2 minus 9. So she forgot to distribute in step 1, forgot to distribute the negative sign to all three terms. So she forgot to distribute it to the 9k and the plus 1. All right, so first part of your homework assignment that you'll actually be doing tomorrow after day 2 will go through some of that Algebra 1 review that you'll need later on in this unit. Okay, so here is another problem. Okay, so Yanni and Shayna manipulated their rational expression, which is a fractional expression. Their responses are shown below. So Yanni came up with 16z squared over 24z squared, and Shauna came up with something completely different. So did either of the students write an expression that's equivalent? So what we're going to do is we're going to take this expression and we're going to simplify it correctly. So the way you do that is you factor out the GCF. Factoring is going to be big in this unit of the numerator. So that would be an 8z. And in the bottom, I have a GCF that is also 8z. So if I factor in 8z out of the numerator, 16 divided by 8 is 2. Z squared divided by z is z, minus 40 divided by 8 is 5. And the z divided by z just becomes 1. Okay, so on the bottom, if I take the 8z out, which is the greatest common factor, 8 goes into 24 3 times. And z squared divided by z is z. Minus 40 divided by 8 again is 5. So now I can cancel off factors. And my answer is 3z minus 5 over, or 2z minus 5 over 3z minus 5. Okay, so did either student write an expression that's equivalent? Yes. Shauna did it correctly. She canceled factors. And that's the only way you can simplify a rational expression is to cancel factors. So she canceled out the 8c's. Okay, so Yanni did something completely wrong, and she canceled out the negative 40z's. Common mistake, but it's completely wrong. She canceled out terms negative 40z over negative 40z. So she tried to do this. And those are not factors, they are terms that are being added or subtracted. So in order to cancel out terms, they have to be factors. All right, so we're going to start off looking at polynomials. We're going to identify zeros when it's written in factored form. Factoring is going to be huge, so if you had trouble with that back in the very first unit, quadratics, you're going to get another shot at it here. And then you're going to understand that if factors multiplied together equals 0 for a specific value of x, at least one of those factors must also equal 0 at that value of x. All right, so we're going to look at this on our calculator. I'm going to pause this real quick and get my calculator started. If you don't have your calculator with you, you might pause this and run and get it. All right, so we're going to put these two equations into our calculator. We're going to compare them. If you notice, it says you may use a calculator this time, so we'll eventually be looking at these kinds of equations, and you should be able to sketch graphs without your calculator once we get a little bit farther into the unit. All right, so grab your calculator, press your y equals, clear anything that is in the calculator, and also make sure your plot up there is turned off. So arrow up and press enter. I pressed enter, it's on, now it's off. Okay, so let's type in the first equation, which is x minus 1 times x plus 2 times x minus 5. And our second equation is the same thing, except it has a 3 in front of it. So x minus 1, x plus 2, and x minus 5. So make sure you use that subtraction sign and not the negative sign. Remember, the calculator doesn't like it when you think a negative is subtraction. And also, if you don't have a color calculator for the second equation, arrow back in front of the y sub 2, you won't have a color there, but you'll have that diagonal line. Press enter one time, and that second graph will graph a little bit thicker so you can see the difference. All right, so we need to zoom to standard, so we're all in the same spot. So press your zoom key in number 6. Mine graphed very quickly. So you can see that all three both equations graph at the x-axis in the exact same spot. So let's change our y maximums. We can see where it crosses 3 different times. So let's change our y maxes and our y mins so we can see the top. So let's change our y max or our y min to -20 and see if that works. And then we'll go +20 for our y max just to see if that works, if we can see the top. Okay, so I can almost see, so let's go back to our window. Change those again. Let's go -40 just to be safe, and +40. Hopefully that's enough. Let's press graph again. Still can't see the bottom of the red one, but that's good enough for us. All right, so if you compare the two graphs, the first one we graphed is the blue one. That's the one without the 3 in front. And the second one is the one that had the 3 in front. So if we go back to our notes, we can kind of maybe sketch these. Let's do it up here. So this one we'll do as red. So it crossed, let's see, kind of look like this. And then the second one crossed at exactly the same spots, but it went a little bit higher and a little bit lower. All right, so the similarities that we see here, it has the same x-intercepts. Okay, so you can see that from these 3 factors being the same. Those are also called zeros or roots. Okay, so those are the values of the x that make the entire function or equation equal to 0. The thing you can see too is this piece of the puzzle is called the in behavior. So they have the same in behavior. We'll talk about that later on too. Both of it is down on the left, up on the right. And your max and mins occur at the same x values. So I have maxes here and here. The x value is the same, but the y values are different. And I have mins at those 2 locations. So they occur at the same x, but the y's are different. Okay, so the differences are the y values for the maxes and mins. Those are different. And the reason that is because of this 3 sitting here. So back in the world of quadratics, we learned that that was a vertical stretch. So that is because of the 3 in front of the second equation. Vertical stretch. Everything else is the same, but the second equation would have a higher max value and a higher min value at those two x locations. All right, so that is all of the notes for today. You do not have an assignment. Oh, never mind. We got one more example. I'm sorry. All right, so has a little cool down. Still don't have an assignment until after tomorrow, day 2 notes. Okay, so we're going to write an equation for a function whose graph is in the xy plane, has x-intercepts at -9, -6, 0, and 4. So if you look back at these, it works the same way as it did for quadratics. Your factors are always opposite of what your zeros are. So this one had zeros at +1, which would be this location right here, -2, which would be this location, and +5, which crosses the x-axis at that location. So if I have x-intercepts at these 4 points, I need to have 4 factors. So I'm going to have y equals, the crosses are at 0 at -9, I'm going to have x plus 9. For -6, I'm going to have x plus 6. For 0, I can do plus or minus 0, doesn't really matter. And for a +4, I need x minus 4. So I'm going to put an a value in front of that, because all the a value does is it's going to determine the end behavior, which is going to be a later concept that comes up. It'll also tell you if that graph is going to be taller for your y values, so vertical stretch, vertical shrink. So if I simplify this a little bit, well, this factor right here just needs to be x. So I can throw that out in front with the a value. And I have x plus 9, x plus 6, and x minus 4. Okay, so there is 1, 2, 3, 4 zeros. There's the x equals 0, x equals -9, x equals -6, and x equals +4. The a value determines end behavior. Again, end behavior will come up in a future lesson. All right, so no assignment until after tomorrow's notes, so enjoy the rest of your day or evening.